So last time we started the slide set for the foundation design. In this Gabi reinforced concrete foundation supporting only gravity loads. Gravity load means dead load and life load. So seismic or wind forces are not included in here. As it says here, gravity and non-gravity foundation usually designed to support all of these loads. The loads will include vertical loads, lateral loads, and moments. Gravity usually, when it comes to gravity foundation, it's gonna have a little bit of vertical loads and some moments from the eccentricity. Lateral loads is gonna be only for seismic and wind forces. So in this course here, I'm not gonna be addressing seismic forces. As you see here, a typical pad supports a column. So the load goes from the slab to the column, from the slab again to the column, is accumulated, and then at the end transferred to the soil through the contact area between the footing and between the soil. Last time I asked the question, I said, what happened if I have no foundation? And everybody agrees that this column here is going to be penetrating the soil, it's going to be just sinking. And the reason was because the soil is unable to take the concentrated stresses right below the column. So the column itself is good. It is able to take the stresses, but the problem is giving the soil. To be sure that this is not happening, we need to be sure that we have enough contact area between the footing and the soil. And the way to do it, by being sure that the stresses is not going to be going above a given limit. And this given limit we call soil bearing pressure. So this stresses right below the footing should not go above the allowable soil bearing pressure. Also, we discussed one of the simple paths or footings. It has a concentrated load coming from the top. Now the pressure here is a resistance. It's going to be like the reaction. And as you see here, the footings are going to start to bend up. So what happens is when this pressure is pushing up, this footing is going to start to bend up. And the main reinforcement is going to be at the bottom of the footing. So footings like this, main reinforcing is expected to be at the bottom, not at the top. But from time to time also we put this top mesh because the minimum reinforcement ratio needed and some other concerns. That was an example for an actual project with the footing schedule. And this is going to be here the actual foundation that we have there. Actual pictures taken there. As you see here, there's no formwork, just the hole was made a little bit larger inside the soil. And then after that, they put the reinforcing. And as you see here, reinforcing on the top is very light compared to the reinforcing at the bottom. In terms of the bar size, in terms also of the number. Now, here's what happened. Footing is poured. And then after this, we have the column rebars sticking up. They put all the ties, they extend the column rebars. And then they're going to start here to form the column itself. And then they cast a concrete column. After that, some concrete slab is going to come here on the top. So to do my design, I'm not talking here about the design when it comes to the reinforcing. I'm talking about the size of the footing. So if you like here to size the footing, again, you need to be sure that the soil here is not going to get penetrated by the column. Like what we said last time, we want to be sure that the acting pressure, like the soil pressure, is going to be within this BC, and BC is the same as Q allowable, which is allowable bearing capacity of the soil. So in order for us to do this, we need to size the footing so that when you take the P surface demand, which means the total dead load and life load with no load factors. So actually, when you do soil design, it's going to be ASD design. There are no load factors, the 1.2 and 1.6, and also 1.4 times dead load. It's not going to be included here. So all what you need to do is just add dead load to life load divided by the allowable bearing pressure of the soil. And with that, you get the minimum contact area of the footing in terms of the plan view, length by width. One example, since the concept is that simple, it says here dead load is 850, life load is 560, square footing is going to be used. Soil bearing pressure, 7,000 pounds per square foot, or 7 KSF. So I can say this gives you the same as, if I may write here, I'm going to say this gives you the same as 7 kip per square foot. And the question is, what is the size of the footing? I have here a few sizes given to me. But it says here square footing. So once it says a square footing, it means it can be this or this. This can be the two choices. This is non-square, this non-square. Total service is going to come from dead load plus life load. So again, what you need to do is to add the dead load to the life load. Now we have about 1,400 kips. The area needed is going to be equal to this given service load. The reason I call it service, because the other one's going to be factor load or ultimate load. When you add the load factors in here, no load factors. So let me write this down here. So just to size the footing, now actually I'm designing here the soil. I'm checking the soil bearing pressure. And look at this. I need 201.43 square feet of contact area. Since this is going to be square, if you do square root of this number, you end up with 14.2. Now my closest choice is going to be 15 feet by 15 feet. This choice is coming from these 4 choices. So I decided to go 15 by 15 instead of 18 by 18. Because it looks like I'm going to be okay. This is closer than. Now look at the square footage here. It's going to be 225. So okay. Maybe I can double check here the stresses if I want to. So I'm going to say, let me check this out. I'm going to be taking here P, with the service load, divided by the actual area provided. This is equal to 1410 divided by 225. Can someone help me with this? Yes? Alex? Hey, Alex?
Yep.
Yeah, can you help me with this? What is the actual stress?
It would be 6.3.
6.3. All right, thank you. So is this okay or it's not okay?
It'd be okay.
Why? What's the reason?
Less than 7.
Less than 7 KSF. Very good, thank you. All right. Now, the previous footing was just supporting vertical load. Now I may have vertical load and some moment. And we discussed the source of a moment coming to some gravity footings. We said it could be because some eccentricity, maybe because we have a corbel. So we have more than one reason to have moment at the interface between the footing and the soil. So we have here 2 sources for the stresses. We have one is given for the axial load and the other one is given for the moment. So to me, I can just deal with each force separately, and then at the end of the day, just add the stresses to each other in the footing. So I'm gonna say first the stress coming from the vertical load. You just take here this P divided by A, very similar to what we have done here. So the stress source here is gonna be just from the vertical load. I have also moment applied on the footing. So I can say here the stress coming from the moment is gonna be M divided by the section modulus of that interface section with the soil. This one here, because the source is coming from the axial load, I'm gonna call it here F sub P. And this one, source is gonna be coming from the moment, I'm gonna call it here F sub M. At the end of the day, I should be able to add the stresses. But I'm trying to understand why it says here F1 and 2. Now, when you have a moment applied on the footing, the stress here is not going to be the same as the stress here. It's going to be like compression and this going to be tension. But the problem is the soil cannot take tension. Once you start here to apply moment on the footing, and if there's no vertical load to balance it down, just the footing is going to be lifting up. And there's going to be a gap here between the footing and the soil. But just for the applied vertical load, you're going to have complete uniform compression stresses that I may call here F sub P. Due to the moment, one side is going to be compression and the other side is going to be tension. Since I have both loads in the same time, I can say the stress here, I may call it here F1 and the stress here is going to be F2. Or maybe this side you can call it F1 and this side is going to be F2. Now you take the stress here at that point, at the first point on the left side, you say I have a stress coming from the vertical load is going to be equal to Fp, is going to be compression. At the same point, I have moment is going to be creating tensile stresses on the soil right here is going to be equal to F sub M. When you go here to point 2, you take this Fp and you take this plus Fm. It means if I have here compression throughout and then this side is going to be compression, it means the stress here at that point is going to be all compressive. I have compression coming from the P and compression coming from the moment. While at this point, I have some compression and a little bit of tension. Now, if the value of the stress coming here from vertical stresses is going to be greater than that coming from the moment and tension, the foot is going to be lifting up. I'm going to have complete compression below the footing. But if I have lots of tension here because the moment value, let's say it was very high, compared to the stresses coming from the axial load, it means that the foot is going to be lifting up. Let me go here through the variables that we're going to be using in our analysis. The vertical load, as you see here, is going to be P. The moment on the footing is going to be M. All service. This A is going to be the contact area between the soil and the footing. Like in our example, if I may go back, it's going to be like this A is going to be 225. This is going to be 15 times 15. It's going to be the contact area or the interface area between the soil and the footing. S is going to be section modulus. Section modulus of this contact area. So in the previous example, if I'd like here, just to confirm my understanding, I'm going to say here A for the previous example. A equals 15 by 15, 225 square feet. While here, this gives you the section modulus resisting the moment on this contact area between the soil and the footing. It's going to be BL squared divided by 6. It just happened that the footing is square. So I can say here 15 times 15 squared divided by 6. Can someone help me with this? Armando, can you help with that?
Yeah, give me a sec.
Yeah, go ahead. You follow me?
Yeah, let me get my calculator.
Okay.
15 squared divided by 6. 37.5.
Why you ignoring this 15? Any reason?
15.
Do you understand this equation first, or have you seen it before?
Let's see. Oh, okay, yeah, I ignored the 15th base.
Okay. Is it gonna be cubic feet or square feet?
It should be cubed.
Right. Very good. All right. So what is this F sub P? Is gonna be the soil pressure coming only from the vertical load component. F sub M is gonna be that component coming from the wall. So okay. So again, in this illustration, it shows here's the pressure, uniform pressure coming under the P force on the footing, and this is gonna be the moment. But in reality, both of them is gonna be acting on the same footing. So this footing, just the same. They are not two different footings. So in value, if F sub P is gonna be greater than F sub M, you're gonna have lots of compression. Like in this case. The pressure is gonna be additive in one side. Additive means, if I may come back here, I can maybe throw an example here if you guys like. So I'm gonna say, I'm gonna call this is gonna be 0.1, and this is gonna be 0.2. I'm gonna throw here some numbers. I'm gonna say P equals 1,000 kip. Area equals, for L equals, I'm gonna say, let's say 15 by 15. S equals 562.5 cubic feet. Now, at both of these 2 points, I can say that the pressure coming from this vertical load is going to be equal to P divided by 225. So it's going to be equal to 1,000 divided by 225. Can someone help me with that? Yes?
$4.44.
Units? Can you help me with units?
Kip per feet squared.
Okay, good stuff. Very good. How about this 0.1 in this side? Is it the same pressure or is it going to be different? Just coming from the vertical load.
Would be the same, right?
It's going to be the same, right? All right. Now, I'd like you to consider some moment. So I'm going to put here some moment value. I'm going to say M equals 200 kip foot. Now, these 2 points, in this point here, I'm going to call it also 1. And the stress here is going to be equal to M divided by S. So it's going to be equal to 200 divided by 562.3 or 0.5. How much is it? It's going to be M over S. Like exactly what we are doing here. Look at this, M over S. How much is this? Can you help us, Sherry, please?
0.35.
1.35,
0.35.
0.35. KSF also?
Yes. Oh, no. Yeah.
All right. How about the stress at this point from the moment? How much this is going to be? So I'm going to call this to be 0.2. How can I do this? You can say this value is the same as this value because in this load case, I don't have any axle load, just the moment. I'm trying to simplify it here. So we can say it's going to be equal to the same as 200 divided by 562.5, right? Is going to be equal to 0.35 KSF. Just the value is going to be different because if you call this negative, it's going to be positive, or the other way around. If you just call the compression to be positive, you can see here tension. Because I want to differentiate between the two stresses. Each one has different value. Now, what I'd like to do here is to come at 0.1 and find out the total stress. Let's say 0.1 total stress, which is this point here. Now I have a stress coming from the first load case of 4.44 compression. So we say, okay, 4.44 plus 0.35. So I have 4 point, and then I have 7.9 KSF. So it's going to be compression added from this value and also compression added from this value. So this is going to be here final stress. Let me write this down next time. How about on this side here? You say, well, let me see. Right at this point, the stress is going to be equal to compression of 4.44. This is what I assume positive. And say subtracting 0.35. It's going to be 4.09. Is this correct?
Yeah.
All right, good. So the stress here is going to look like trapezoidal distribution, actually. So the final stress that you should expect is going to be something like this. This side is going to be more compression. This side is going to be less compression. It's going to be like this. So in this side is going to be 479, and this side is going to be 409. So numerically, M divided by S was lower than P divided by A. This is why the entire foot is going to be under compression, and the foot is not going to be lifting up. The problem is going to happen when you have lots of moment and then you have less axial load or vertical load. Now, you cannot balance the footing because now the footing is going to start to rotate. It's going to be to lift up. And a gap is going to be happening between the footing and the soil. You don't like to be in a case like this. You'd like to have enough vertical load to stabilize the footing compared to this moment action. Any questions? You're good? All right. So here's the first case that we have studied already. This one, F sub P in value is more than F sub N. Exactly what happened. Look at the stress here, 4.44 compared to 0.35. Yes, greater in value. It means footing is not lifting up, and the way I've done the analysis here is good. So I'm done. The other problem is going to happen again when F sub P is going to be lower in value sub F sub N. Means I have lots of rotation, and the footing is going to be start to lift up. When the footing lifts up, the actual stress distribution is going to look like this. Because the soil cannot take any tension. So if this is going to be lifting up, so distribution is going to look like this. Like in this case. So here's the first case. You have both compression on both sides. Maybe one side is going to be greater than the other. which is okay. Now what I need to care about, that this pressure, F sub 2, doesn't go above the allowable value. This is what I care about. But when you have here big moment, and the foot is going to start to lift up, it means there's no contact here between the footing and the soil, and the foot is going to be lifting up, and this is going to be the stress distribution for this on the footing due to this vertical load and moment. Now, in this case, I can take it here, just enlarge this and put it right here. Here's the stress, maximum stress. And the point load that's come from the top, if you take this P and M, convert it into P and E, since E is going to be equal to M divided by P, very similar to what we have done in the past. When you have eccentricity on a column, moment equals P times E. Now, in my case here, I can say E is going to be equal to M divided by P. Now I have the eccentricity on the footing. If this is going to be right in the middle of the footing, it means that I have here the length 1 by 2 and the length 1 by 2 because it's going to be right in the middle, and E is going to be measured from the center of the footing. This distance from the point load to the end, I'm going to call it here X. And this X in equation is going to be equal to 1/2 of the length of the footing subtracting E. It's right here. 1/2 of the length subtracting E. So again, I have this vertical load and I have some stress distribution. This point load is given equilibrium with this stress distribution comes from the bottom. The problem here that we're talking about in this case is how to balance this vertical load with this pressure coming from the bottom. If you like to take the moment about the point here, let me point at it. Let's say here. If we are saying here, this pressure coming down like this, multiplied by the distance from this point to the point of application, is going to be equal to the pressure coming from the underside of it. If I do here summation, if I do here result of the pressure, and this needs to be balanced, needs to be aligned with this pressure here. Therefore, the resultant of this stress distribution and is going to be in equilibrium with this vertical force. So great. So, and this resultant is going to be at 1/3 of this phase length because it's going to be the CG of this shape. So if this to be X, this has to be 3 X's. In any given problem, the vertical load is going to be given to you. Moment also is going to be given to you, which means that you can figure out E. So this E is a known value. The length of the footing, you have it. Therefore, you can figure out X numerically. Once you find X, multiply by 3, now you have the base of this stress distribution. This resultant force is going to be equal also to P. Because if it is not equal to P, it means that the system here is not in equilibrium. And it's going to be just fading. So this force here, it has also to be equal to P. So if you take here summation of the force to find out the resultant force, which is P, you just set it equal to that P, you can figure out the amount of stress. How do you do that? Now let me write the equation, try to set the given vertical force P from the top equals. It's going to be equal to F sub 1, the stress value, times 3x multiplied by 3x. Divide this by 2, which means the area of this triangle. And then at the end, multiply by the width of the footing in the other direction, which is B. Does everybody follow me? You guys are clear on that? Yes? Any questions on this concept?
Could you repeat the P part again?
Okay. I'm trying here to balance the two forces. One force is come from the top, one force as the reactions come from the bottom. How do you balance it? You said the resultant of this stress or pressure distribution is going to be equal to this P. Come from the top, I have this force P. From the bottom, it's going to be the area of this triangle distribution multiplied by the width of the footing, which is B. So I'm going to say here P, which is come from the top, equals B, the width, times the area of this triangle. The area of this triangle is going to be F1 times 3x. So in my equation here, what do I know and what's missing? I have the width of the footing. I have x. I just was able to go through the values and figure out x. I have the vertical load that was given to me, P. I can figure out here F1. And this is how we ended up with this equation. Any questions? Hello?
I have a quick question.
Yes.
So when if the footing is only using half of the footing for the force, does that mean the footing has to be bigger for the soil because of the penetration?
When you have moment, the footing needs to be larger. This is given, okay?
Okay.
You mentioned here half of the footing. Is it because I divide here by 2? Is this the reason?
No, the L/2. When the footing lifts up, it's only using L/2 as the
In the analysis to figure out x? In
Well,
here, in this equation?
no, just in reality, like when the footing lifts up,
In
you're
real, yeah,
you're only
I
using
see
half
your
the
point.
column.
No, not really half. You're using a fraction of it. Because
Okay.
look at this line here. It is
Okay.
not necessarily to be 1/2. It could
Okay.
be maybe 10% here, 20%.
Okay.
Very good. I have one example. In this example, I'm going to be here working with the stress values, and I'd like to try here the two cases in the same example for the same footing. So I'm going to be here keeping the vertical load to be the same and working with or playing with the value of the moment applied on this footing. To do this, I need to split it into two examples. That's why it says examples 2 and 3. Footing size is 12 by 10. Here's the axial load, some moment. And look at the moment direction. Moment direction is going to be about this axis. So when it comes to the area is going to be 120 square feet, the contact area. It's like plane and it's going to be like the elevation or the side view. But when it comes to the moment, it's going to be about this axis. So the S value, if you like to try here, I'm going to say here the S equals BT squared or BH squared. B here is going to be the 10 feet times 12 squared divided by 6. Is going to be the section modulus because moment is going to be happening this way. They say here the surface vertical load, which means dead load plus life load, is equal to 600 kips, and the moment is 720. And you'd like to find out the stress distribution below the footing. So the first example, we just asked for the maximum soil pressure under the footing. I understand that one side, which means this side here, I'm going to have higher stress and compression than this side because the moment is lifting the footing up. So the first one just asked about the maximum soil pressure. The second one, they said, what happened, this is gonna be example 3, if the vertical load is reduced. So at the beginning, I have vertical load of 600 and the moment is 720. So the values is kind of okay in terms of the footing design. But now all of a sudden you reduce this vertical load. So the moment value compared to the vertical load is gonna be big. And in this case, the footing may be lifting up. So this is the reason that I have here 2 examples. So in the first one, I'm expecting that the soil is gonna be in full contact with the footing. In the second one, the footing is gonna be lifting up a little bit and the pressure may reduce on the left side. So here's the first example. 600 kips. Here's the moment. I have length and width. Contact area of the soil is gonna be 120 square feet. This footing here is actually the S value for it is gonna be 10 times 12 squared divided by 6, 240. I have here the pressure is gonna be coming from 2 sources. One of them is gonna be this vertical load, and the other one is gonna be the moment. So from the vertical load, it's gonna be P over A, 5 KSF. So this F sub P is gonna be 5 KSF. And from the moment is gonna be M over S, 3 KSF. So on this side here I have 5, and here I have 3 and 3. One of them is gonna be tension, the other one is gonna be compression. So when you have here 5 and then you have here 3, you end up with 8 on this side. And on this side, you have 5 subtracting 3, you end up with 2. Exactly what happened. Are you guys following this example clearly, or are we good about this example?
Yeah.
Okay. So because of the relative value here between the compression versus the tension on the side, I have here 5 KSF, and here I have 3 and 3. So maybe I need to write this down. Let's see, here I have 5 as compressive stresses, and here I have 3 as in tension and 3 as in compression. When you add 5 to 3, it's going to be 8 on this side. And 5 minus 3 is going to be 2 on this side. Okay, so exactly what I'm getting here. F1 and F2. Yeah. Okay. So the maximum stress below the footing in this case, the answer is going to be 8 KSF. I have more than one value for the stress distribution. One side is going to be 8, one side is going to be 2, and the problem in number 2, it says maximum soil pressure. I'll give you the highest value. We're just hoping in this specific problem that we're not going to be going here beyond the allowable soil bearing pressure, even though in this problem here, it was not given. And all what I need to do is just find out the pressure under the footing. Any questions on this example? We're good? All right. Now, in the following example, I'm gonna have here the axle load drop down from 600 to 240, but the moment stayed the same. Contact area is gonna be the same. Section model is gonna be the same. Doesn't change, it's gonna be the same footing. The pressure coming from the vertical load is gonna be 2 KSF. Now the pressure coming from the moment source or the moment side is gonna be 3 KSF. Now it is larger than that. So now I cannot use this equation. What equation? I cannot use this equation that says you add one side, F2 is gonna be the pressure coming from here plus here. You can't really do this. You need to use this equation. You need to find out the eccentricity. Your eccentricity here is 3 feet. Why? Because you have 720 moment and 240 axle load. So you have here 3 feet. Total length of the footing here was 12 feet. You can say from here to there, L equals to 12. Subtracting 3, right? Of course, after you divide by 2, you'll end up with 3 feet. So let me put these numbers here. You can say total footing length is 12. Therefore, this is going to be 6 feet. And this side here, I have also 6 feet. E, based on this analysis, M over P is going to be equal to 3 feet. I have 6 minus 3 is going to be another 3 feet for the X value. Let's say this X will be equal to 3 feet. All right, now I have this equation, which I just copied from here. I just may go back. You see this F1 based on equilibrium of the two forces. So look at the equation here. F1, 2/3 of P, which is 240 kips coming from here. 240 kips divided by X, which is 3 feet, divided by the width in the other direction, 10 feet. You have 5.33 kSF. So this stress here is going to be 5.33 kSF. Any questions? I guess now we see the two different examples. In one of them, vertical load was a lot compared to the moment. In the second one, moment is a lot compared to the vertical load. So when you have more vertical load compared to the moment, you may end up with distribution like this. When you have less vertical load compared to the moment, you may end up with lifting up of the footing, and the stress is going to be here because the soil cannot take tension. Would like to hear any questions? Yes? No questions? Okay. What is this combined footing? Combined footing when you have one footing supporting two columns at the same time. And it could happen. When columns are kind of close to each other and the footing size is kind of large and they are overlapping together, this one you have here, this combined footing. It's going to look like this. This like plan view. So you have one column, another column, and each one of them, they have different dead load and life load, but they're kind of close to each other. So the question is, how can we design the contact area between the footing and between the soil? I don't have here any external applied moment on these two columns. I just have the axial load. As you see here, C4 supports 850 dead load, 400 life load, total of 1250 as service load. C2, you just add this two number, it's going to be 1,000 kilo. The allowable soil bearing pressure is 8 kSF, or like 8,000 psi. The column spacing is 8 feet. This means from here to there, right? This is going to be 8 feet, center to center. So, okay. Now, what's the question? It says the footing dimension, length by width by thickness are. Pick one of these. It depends, of course, on the soil pressure, right, that you're trying to keep. So let me go back here again, just confirm I have here 1250 and 1,000. This footing supports both of these two loads, meaning just add the loads to each other. Here's the first load on the left-hand side, is going to be 1250, and this one, C2, is going to be 1,000 kip. Total load, which is going to be right in the center of the footing, is going to be 2250. Just add these two values to each other. Now, how can I come up with this? Contact area needed. Contact area or the footing area needed, you just take the vertical load divided by the allowable pressure, the 8 kSF. I need 281 minimum of contact area between the footing and the soil to be able to make it work at 8 kSF. The appropriate footing size is gonna be here 12 by 24. This is what I'm gonna be going with. How's that? 12 by 24 will give you 288 square feet. You need minimum of 281. So this is good. So this footing size is gonna be good. 12 by 24. Now, these two loads are not the same. This is a little bit heavier than this. This resultant force, the total force 2250, it's not going to be right in the middle. It's going to be shifted a little bit to the left. It's going to be shifted towards the larger value of the force. If I have 1,000 and 1,000, it's going to be right in the middle. But because I have 1,000 and 1250 to the left, this resultant force is going to be coming this way. Now, someone here is going to be looking at this and say, you'd better put this resultant force location to be right in the center of the footing. So the footing size that I picked here is going to be 12 by 24. The spacing again between columns is going to be 8 feet. I'd like to put this resultant force location, which I can figure out, to be right in the middle of the footing. Because someone here can come to this design. Let me show you exactly what I'm talking about. Here's the footing size. And just decide that this is going to be right in the middle. It's going to be like this, meaning 8 feet, 8 feet, and 8 feet. This can be one option. So let me write it down. Someone can come here and say, okay, this is going to be 8 feet. And here's going to be another 8 feet. The middle, we're going to have 8 feet, total of 24. But in this case, this resultant is not going to be in the middle because the resultant is shifted a little bit left. So the thing is, to keep the resultant in the middle of the footing and avoid any moment in the footing, I just need to shift this little bit left. So that the center of this red box is going to be right in the center of the resultant force. It's going to be aligned with it. As you see here in my analysis, I put this to be 8.5 and this going to be 7.5, which means I moved it 6 inches, like half a foot, just to make it simple and to avoid the moment on the footing itself. So my target here is to find out location of this resultant force, the 2250. Where does it happen? And this location here is going to be right in the center of this footing. Any questions?
I have
No.
kind of a general question.
Go ahead.
Why do we not count the weight of the footing itself in the allowable pressure on the soil?
Okay. When it comes to the soil pressure, we have 2 ways of doing it. We have the net and then we have the gross. Are you aware of that? Gross and net?
Nope, but now I am.
All right, okay. Let me tell you what's happening. In some soils reports, if they say the net pressure is going to be, let's say, 8,000 KSF, it means it's okay to ignore the self-weight of the footing. If they say gross, it means you need to include it. So you're absolutely correct. It should have been included in there. But it was ignored because this value here is going to be net. But if you like to do detailed analysis, you need to include the weight of the footing. As a matter of fact, the next example, we're going to be including it. And you're going to see this for yourself.
Okay, thank you.
No problem. Good question, good comment, Al. Is it okay? I'm trying here to avoid any moment on the footing. So the way to avoid it, if I put the center of the footing to be aligned with the resultant force. Let me find out here the resultant force location. I'm gonna say, okay. This distance, if I may enlarge the picture a little bit, from the resultant, here's the resultant, to the left column, the 1250, I'm gonna call it here X1. In statics, to find out x1, you take the moment about this point for these two forces. How do you do this? You come here and then you say 2250 multiplied by x1 is going to be equal to 1000 multiplied by 8 feet. Here we go. 1000 by 8 feet equal 2250 times x1. Now x1 equals to 3.55 feet. It's about 3.5 feet, 3.5. This is the reason I shifted the footing. If you remember, the footing used to be like this, right? And then I shifted it half a foot so that this vertical load, the resultant, is going to be right in the middle of the footing. How do I come up with this? Or how did I come up with this half a foot? From this analysis here. If this is going to be here 3.5, how much is this? It's going to be 4.5, correct? This means that this resultant force has been shifted by half a foot. So here's the middle of the footing. Excuse me. This is going to be the, I'm going to see here, center line between the two columns. This is going to be here at 4 feet and 4 feet. Now, from the first load, column C4, to the resultant force here, 3.5. But this column is going to be at 4 feet away from the center line between the two columns, the midpoint. This means that this resultant, because of the relative difference between the two vertical loads, has been shifted by 6 inches, like half a foot. So again, what should I do? Just shift this footing. It used to be like this. You see here, see this white box? You just need to shift it here, half a foot. So now this cantilever length, I'm going to make it larger than 8 feet. You remember when I have equal points, 8, 8, and 8. Now it's going to be 8, 8.5, and then this is going to be 7.5. So I have here I have a foot that I took from the right cantilever, put it on the left cantilever. Now, in a case like this, the pressure below the footing is going to be simply equal to the total force divided by the total contact area. How much was the total force again? 2250. Contact area? Let me check. Contact area is 288. Now let's take here for the actual pressure. 2250 divided by 288 is going to be 7.8, and this is okay because it is lower than 8 KSF for the net pressure. Questions? All right. If this is going to be the center line between the two footings, it means this is going to be half a foot, right? But when I look here at this one, it is true that this is going to be 3.5, but the calculation says 3.55. But I can't do this in construction. I need to go to some good numbers. 0.05 of a foot shift is not really a big deal, but 0.5 a foot, yeah, it makes a difference in my analysis. So in this case here, footing is going to be right here, right? But the actual location of this centroid of this resultant force is not going to be right in the centroid of the footing. Actually, it's going to be shifted. And the question is by how much? You see difference between this white little box to the footing. This shift here, or this spacing, is going to be actually equals to 0.05 of a foot. So I still have a little bit of a moment, but the moment is going to be very small. Why? Because E is very small. I don't have E of, let's say, half a foot. It's going to be 10th of that, 0.05 of a foot. So it can be disregarded if you like. But if you decide to include it, if you like to go very exact, you're going to say, here's the eccentricity that I have, which is about 0.05 of a foot. Now you're going to have M over S, and of course you have P over A. Your P over A is going to be 7.8. The moment that you have is going to be 0.05 multiplied by 2250. Small moment. And here we go. M over S, the stress coming from the moment source is going to be 0.1 KSF. Look at the one coming from the vertical load, 7.8. So I guess this can be very small. You can disregard if you want to. But if you like, again, to go in detailed analysis, one side is going to be 7.9, other one is going to be 7.7. Why is that? Because it is here 7.8. One side is going to be going up by 0.1, the other side is going to be going down by 0.1. It's going to be 7.7, 7.9, still below 8 KSF, and we're in good shape. Questions? No questions?